All right, hi. I am Jordan, and I am at the University of Pennsylvania with Conrad Cording. My charge is to give a slightly inflammatory talk, only moderately inflammatory, and say things that are annoying but also useful and true. And so if the words brain emulation feel annoying to you, you could replace them with forward prediction. Yeah, exactly. We all have to take the annoying but true class. But okay, let me start with some true things that aren't annoying, and in particular, I want to talk about scaling. Here I'm showing some of the recording technologies that we now increasingly use, like electrophysiology, and now the new emerging optical recording, and these technologies are growing extraordinarily quickly. So this is really exciting. The other good news is that the brain is not growing extraordinarily quickly. So the number of neurons that we're going to have to record from at maximum is staying roughly the same. Unfortunately, so theoretically, like these lines will intersect with like 80 to 100 billion neurons at some point. But as it turns out, the doubling times of these systems are actually rather long. And if we were to wait for electrophysiology, I mean, people will debate these exact numbers, and I'm happy to talk about the precision of these numbers, but you could expect on the order of centuries for electrophysiology to record from every neuron in humans. Optical recording, better, a doubling time of maybe 2 to 3 years, but we would still expect probably 40 to 50 years. So that's a more accessible timeline, but like certainly not the timelines that we'd like. On the other hand, structural imaging is also scaling very, very quickly. We're seeing many orders of magnitude in just the past few years. This figure is, with apologies, just electron microscopy, but of course expansion microscopy is exploding that, and E11. I'm wearing my E11 socks. I don't have any electron microscopy socks. But hell yeah. And so there's this trajectory where we're imaging things that are roughly the size of a human brain in order a handful of decades, maybe even shorter. And so the thing that I'd like to propose here is that maybe we need to be talking about the trajectory to understanding recording of neurons and function through structure. That brings us to this problem of structure to function. Here is a formalization of the structure to function problem, which is one of the things that I think is holding back a lot of the work that should be happening in this space but cannot yet happen. Here I'm showing increasing amounts of molecular annotations of a synapse, although you could stand in any old chunk of a membrane here. And as I increase the amount of molecular annotations that I have, I can increase the ability to cluster similar functional systems together. So this is good, and we can start to do this now. But I want to remind you that as we increase the amount of information that we have about the molecules that are present at a synaptic site, for example, the compatible potentials, in other words, the sorts of things, can I stand on that side?
Yeah, you can.
All right, let me try that so I'm not standing in front of my labels. As the number of molecular annotations goes up, the total compatible potentials with that system, given all of our observables, goes down, and ideally you'd like to be in a case where you know exactly the potentials that are coming out of a system if you know all the molecules that are in it, or some adequate set of molecules that are in it. But of course we don't have that function, right? This is not... We don't know the function that takes you from the molecular annotations to the evoked potential. Right? So while it is true that you could be narrowing down the sets of potentials that you can encode for, we don't have that structure to function map. Okay, well this from a few seconds ago, you may remember me saying we don't have this function that maps structure to function. And this is the critical thing that I'm proposing that needs to happen next. We need a function that takes in molecular annotations and tells you how those individual molecules impact the transfer function of the neural system. This is critical, and as far as I can tell, it's missing. But I think everybody in the room wants this to exist. Now I have to go back over here. Okay, I also want to talk in my remaining maybe negative 10 seconds about the... What? Okay, good. I want to talk about the role of perturbation. So as we're recording from neurons, we can start building really, really good correlative maps. But every time you have coincidences in the nervous system, and this happens an awful lot because nervous systems are redundant, you lose all of your ability to do causal modeling. And perturbations solve this problem for you. So the way that you perturb a system is you push it out of the manifold that system lives in naturally, and then you watch how it comes back into the manifold. And this orthogonalizes the correlations between neurons that were otherwise coincidences, and gives you access to much higher information density for a much lower cost. So here is a plot that we put together a few years ago that shows a simulation of C. elegans, plenty of caveats. This could be off by an order of magnitude in either direction. But you can see that the way to read this is that if I want to record and get low prediction error on predicting the adjacency matrix of a connectome, then I need to either record the yellow line I could record for millions of data points for days and days, or I could record from just a few seconds, but with tons of perturbations, and I can get similar prediction error for much less work. So in closing, I want to encourage everybody to be thinking about these problems. How could you be using perturbations to reduce your data cost? And in particular, how can we think about this calibration problem to get from structure to function? And I'll close by saying that this is a project that I am super committed to, and if you'd like, I'm happy to chat privately afterward about a team that I'm putting together and starting to think about fundraising to solve this problem at a molecular level. Thank you.
Thank you. There's like one thing getting the adjacency matrix, but how do I think about getting like plasticity rules? And would you want to do molecular approaches, or would you want to do perturbation approaches?
Yeah, I mean the question is too hard for me. but if I mean it's too hard for me today. But I think the answer, I mean the real answer to that question is, where do you think plasticity where do you think learning happens? Is that implemented in spikes, or is that implemented in molecules? I am of the very slightly dogmatic but also slightly confirmed opinion that this has to be implemented in molecules somewhere. Like this is not just like a function of like the dynamics of the system. So my opinion is like if you're not annotating molecules, you have no hope. I don't know that it's sufficient, but it's certainly necessary.
Alan.
Well, yeah, you sort of answered my question. It was very similar, but broadly, I think the question is, do you think antibody labeling is ever going to be enough, or do you need to know information and phosphorylation state? And so, what is the technology that you wish existed to solve this problem that does not?
Yeah, I mean, so on the one hand, the technology maybe doesn't quite exist. I mean, certainly anytime you put pigments into a cell, you are like changing the cell, right? And my ideal would be that you can like magically read these things out without putting new molecules into neurons, which is of course just maybe that's true. If somebody knows how to do that, please let me know. But I think that what I would hope for in the near term is that we can start to accumulate enough data to start like fleshing out this problem. Because like right now we have like no information about this function, right? I mean, we have like correlative information about this function, but like that's not quite the same. I think even today with antibody staining, or even really clunky older technologies, you can start to flesh this problem out. And I would like to see how close we can get before we start needing to invest heavily in new technologies. But I'd like to see that too.
Last question.
So I was wondering about the effects of physiological phenomena that we don't typically associate with neuronal activity, like glia and neurovascular coupling, perineuronal nets, things like that, and how much you think that influences, and even like long-term genomic changes, gene regulation changes. Like how much do you think that's going to influence your models, and how far are you into trying to figure out how to take that stuff into account?
Yeah, I mean, like, it's a great question, and like I'll make it slightly worse by sharing my favorite example of that, which is that there was this paper, I think now 6 or 7 years ago, that points to neurons like writing down notes on RNA and then like putting it in a vesicle and like giving it to their neighbors, and like, oh no, like that's really hard. Yeah, and it's like, this is great, and it like makes perfect sense that cells do this, but I mean, this was in mammalian tissue, right? And it's like, okay, if we didn't have any, we were like really struggling with, predicting like forward prediction of action potentials, and like now we're throwing in something like RNA is like Turing complete, right? Like, I mean, they could be saying anything in those messages, right? It's really freaking me out. I think that like, this is a really strong argument for not putting our super tight constraints on this problem. We shouldn't be thinking about neurons as a system that like manipulates membrane potentials and that's it. That's simply not the case. And we know that like, if that's all there was, our models would do way better. So I think that the answer is that we should be doing this sort of like, molecular staining, and we should be thinking about cells as ensembles of molecules, but that includes also we should be staining things in glia, and we should be staining things in the periphery and intracellular space around synapses, and like that makes the problem way, way, way harder, but like also conveniently like probably is going to solve the problem better than us, ignoring those things.
Thank you so much.